Hello, Hubble Huggers. It's time for another Hubble Hangout. I never get tired of saying that. My name's Tony Darnell. I work at the Space Telescope Science Institute, and we are about to start another, sort of a new series in Hubble Hangout land. We were talking a few weeks ago, and my guest here today, which is Dr. Frank Summers, is the outreach astronomer. Hi, Frank. Welcome.
Hey, how's it going?
Good, thanks. So Frank and I were talking the other day, and Frank reminded me that every month he does this. He hosts a public lecture series at the Institute, where it's held on the first Tuesday, right, of every month. Is that right?
Yeah. The first Tuesday of every month, we get a different astronomer from either inside the Institute or a visitor coming, and we get them to specially prepare a talk that is more general. And specialized to present to the public, so they get to talk about their scientific research. But we, remind them that all right, you got to start from the basics, get the public, bring them up to speed. But you get to go from sort of the basics of a topic all the way up to the current research that they're doing.
And so I have here, so I put the link to our public lecture series is on the event page, as well as there's also a link to the archive of past webcasts of the series as well. And as part of this, and here you can see a picture of Frank. What are you doing there? Is that like a shadow puppet thing, or what are you doing?
I think
shadow puppets.
I think when they got that picture, I wasn't prepared for it. First of all, that wasn't posed. I guarantee you that. But all I was doing is I was counting off. Okay, 1 reason, 2 reasons, 3 reasons. So I was saying, well, 1 is this, and this looks like I'm on number 2 because I got the second finger, and I probably was doing 3 or 4 different things.
It looks like you're trying to make a bunny rabbit to me, but anyway, okay. Well, I'll take your explanation for now.
Okay, actually, what I'm doing is shadow puppet of an accretion disk around a supermassive black hole.
There you go. That's it. Now, see, you're not the outreach astronomer for nothing. That's called quick thinking right there. Okay, so anyway, the idea was we were talking about this, and Frank gives these prior to the lecture. He gives a little presentation of his own where he introduces some new things that are happening both in the world of Hubble and in space science and astronomy in general. And so he said, why don't we do this in a hangout so that we can make it available to more than just the people who show up at the Institute. And so that's what we're here to experiment with today. We're going to try this out and see if you guys like it. And if you do, if you respond well to it, we will continue doing these probably on the Wednesday following the public lectures that happen on the first Tuesday. So let's try to look for those. Let us know what you think of this. If you find it useful, if you find it interesting and you want us to do more, we'll be happy to keep going. So how do you tell us what you think? Well, this is the land and world of social media, so you have more than enough ways to interact with us. If you comment on the event page, which this is being broadcast from on Google+, we will see those comments. And so if you have any questions for Frank also, that's a good place to leave them. We're also monitoring Twitter and the YouTube comments that we're broadcasting from the Hubble Space Telescope's YouTube channel. So those are all the different ways you can interact with us, and you can also try Semaphore, but I may not see that. So let us know what you think. Comment, leave us some comments and questions, and we will sort of listen to what you have to say as far as whether this was something you found useful. So Frank, let's go ahead and get started. What do you have for us this week? So you have some stories that you think are particularly interesting for this month. So why don't you go ahead and introduce them to us?
Okay, so what I do every month is I try and come up with news from the universe, which of course has to be Hubble-centric because, hey, I get paid to talk about Hubble, right?
That's right.
That is my job, but I don't like it only being about Hubble. So when there are other cool stories that aren't necessarily Hubble-centric, I sort of sneak them in as well and show off all the pretty pictures and try and explain the science. So let me do my screen share. All right, and get to my PowerPoint. And there we go. All right. So this is the presentation that I present. It's called News from the Universe, and as you can see, this is for September 2013.
No, you're not doing it right. You have to go News from the Universe.
Universe.
Nice reverb. All right.
Well, you need 2 people to get that reverb in there correctly. All right.
News from the Universe.
And I also have a lot of fun with it, okay? Because my first story, the top story tonight, is called Lunatic Fringe.
I love it.
And it plays off on both words, lunatic and fringe. And the fringe part comes from, we're talking about the solar system, okay? Now, can you see my mouse pointer on this, or do I have to use something?
I can see it,
You can
and
see it.
it's
Okay,
being
so
embiggened, so I think it's showing up.
embiggened. He's using the Simpsons word. Okay, so down here toward the sun in the center of the solar system, all right, not even shown on this plot are Mercury, Venus, Earth, and Mars. They're way down tight in, grouped in around the sun. And what we've got in this plot here is the orbits of Jupiter, Saturn, Uranus, and Neptune, and also the former planet Pluto, which, as you can tell, one of these things is not like the other. It's easy to tell which one is Pluto. So the fringe aspect of all this is that we're going to talk about things out at the fringe of our solar system. And the lunatic comes in that you may remember that Hubble has actually been studying Pluto really carefully, prepping for the New Horizons mission. Because the New Horizons mission is the first space mission to go past Pluto, and it's going to get there in about 2015. It actually was launched in, what, was it 2005 or 2006? Do you remember, Tony?
I think it's about 2006, I think. I'm not totally sure.
Yeah. And I think it's 2006 because I remember 9 years to get to Pluto, right? And so we've been studying the Pluto system with Hubble because Hubble has the highest resolution to try and see what we could see. All right, and on this slide here is sort of a summary of what Hubble has done. What was known before Hubble was that there was Pluto and its first moon, Charon. Although I got to say, a lot of people consider that a double object because they both orbit around a point in the space in between them. But we're not going to talk about that today because that gets, once you start talking about Pluto, people get all over the place. Have you done a thing on Pluto, Tony?
Well, it is the lunatic fringe after all.
All right, there we go.
No, we haven't actually. We did have Mike Brown on Hangout LAS in January where we talked a little bit about it, some near Earth objects and exoplanets as well. So yeah, we've done a little on Pluto.
So what Hubble has done is it's discovered the other 4 objects here. It discovered in 2005 Nix and Hydra, all right, and then in 2010 it discovered what's called P4, and then in 2012 here it discovered P5. So Hubble, with its high resolution, is the only telescope able to see these really fine, tiny objects out around Pluto, so that we can prepare for the New Horizons mission. All right, and so I've talked about this before, or at least with my public lecture series audience. But the update today is that P4 and P5, of course, are just temporary names. And
I don't know. That was kind of catchy.
Well, they are just temporary names, and they held an internet contest to rename these and give them permanent names. Now, Tony, do you know what name won the contest?
Yes, it was Vulcan, I believe, right?
Yes, it was Vulcan from Star Trek fame.
Yeah, that's
right.
So,
in the first of the reboot of the Star Trek series, Spock lost his home world, so they're trying to give him a new home world around Pluto, right?
Yeah, it's sort of a downgrade, but yeah.
Unfortunately, Vulcan had already been used in astronomy. It was in the late 1800s when Urbain Le Verrier, the French guy who had, along with John Couch Adams from England, had predicted the existence of Neptune, all right, by perturbations in Uranus's orbit. Well, Le Verrier was studying Mercury's orbit and noticed that Mercury's orbit didn't obey the laws of Newtonian gravity, right? It actually shifted a little bit, and that he could account for it if he postulated a planet interior to Mercury, closer to the sun, something that was so close to the sun that astronomers hadn't observed it because the sun is so bright, right? Actually, later it turned into a group of small group of planets, Vulcanoids, out there. Okay, and so they called this unknown planet Vulcan. And when it became about a dozen or 20 planets, they called them Vulcanoids. So Vulcan had already been used in astronomy to explain the change in the orbit of Mercury. Of course, the orbit of Mercury wasn't explained by a planet interior to Mercury. It was actually explained by general relativity.
That's right.
Because the precession of the perihelion of Mercury is due to general relativistic effects for Mercury coming so close to the mass of the sun. So we couldn't use Vulcan for the names for a name of P4 or P5. Instead, we wanted to keep with the gods of the underworld theme with Pluto and Charon and Nyx and Hydra, which are all related to the underworld. So the new names for P4 and P5 are Styx and Kerberos. Kerberos being the three-headed dog, and the river Styx being the river that you have to cross as you go into the underworld.
Yeah, and for all the computer nerds out there, it's also a security ticket that one has to get to access certain file systems on your computer, but that's a separate issue. So,
and of course, those of us our age recognize Styx as the rock group, which I remember going to see them in my senior year in high school.
I know. My very first planetarium show, and maybe even Carolyn, who's out there, I think she's still watching, may have even seen it. Back when I was working at a high school planetarium, I used, what is it, Come Sail Away, I believe, in one of my very first planetarium shows I ever made. So yes, Styx has the rock group Styx has a special place in my heart. So.
All right. So the way I like to refer to these things is they're small, icy objects, and they're all out in the Pluto's domain in the underworld. Okay. So you can look at these as literally being snowballs in hell. All right.
All right. Oh God. Did you take a lot of time thinking that up?
I did. All right. What happened to my? All right. So, but Pluto isn't the only object out there. We also have been studying another lunatic fringe in terms of Neptune. Okay. Now, this image.
Before we leave that real quick, I want to talk just. Can we go back to the contest real quick about why? Why you said we couldn't use Vulcan? So my question is, why was it given as an option, or was it a write-in candidate? And if we couldn't use it a second time, why did they make it as one of the things you could vote for?
I don't think it was a.
So it was written in or something by people.
I didn't monitor the vote very carefully, but you know how the internet is. When people get something in mind, right? And Vulcan, with its fame from Star Trek, once it gets up in the voting, people are gonna continue to add to it.
Yeah, and I think if I remember right, William Shatner had a campaign to get it going as well.
That's right, Shatner.
He got involved in getting it popularized too. I think so. That's probably a big reason why it won. But it kind of means it was a little bit rigged, because the IAU, which is the body responsible for giving things names, was never going to pick that one, since it had already been used, right? And
so that's why the astronomers who ran the who ran the contest basically apologized afterwards, saying, "Sorry, we couldn't use this. We couldn't even propose it to the IAU." Right. So, in a sense, it was a lot of fun, but unfortunately, the contests of the naming things isn't done by popularity; it's done by the IAU. What criterion do they have, by the way? Do you know when they name things? Basically, the astronomers who discover it get a chance to propose names. And for Pluto, they want to keep with the mythology of the underworld. Okay. And so they want to find characters associated with the underworld that they can propose. Okay. For example, for the moons of Uranus, right? Mm-hmm. It's actually characters from Shakespeare's A Midsummer Night's Dream. Yep. All right. Miranda is a character from Shakespeare, right? Mm-hmm. It's one of the moons of Uranus. So there are certain themes that we've used, and they try to stick to those themes. Now you'll notice that Nyx and Hydra both come from underworld themes, but what are those initials, N and H?
Yeah, I don't get it.
N and H, New Horizons.
Oh.
So the guys, when they proposed that, they were very smart. They found two N and H, right, which commemorates the New Horizons mission. I mean,
so a little bit of marketing there, a little bit of NASA marketing going on.
And Pluto is historically marketing. The PL symbol for Pluto was often attributed to being for Percival Lowell, who funded the search for Pluto at Lowell Observatory.
Oh, I didn't know that. Now, by the planet symbols, you mean like there's these little symbols that every planet in the solar system is given to kind of mark it on a star chart or whatever, and that symbol that you said was sort of an homage to Percival Lowell.
Yeah.
Wow, I didn't know that. That's really cool.
I believe it was intentional, but I'm not when they made the symbol that it was intentional. I can't tell whether the choosing of Pluto was intentional to try and honor Percival Lowell, who, by the way, his predictions of the existence of Pluto were incredibly wrong. I mean, they're just totally wrong.
That poor guy was wrong about a lot of things, but he did get some.
I always make
done.
sure that Clyde Tombaugh gets all the credit for it, okay? Because he really did. His amazing search was what's really important about discovering
I know
Pluto.
that, and he was a nice guy too. I actually met him once in New Mexico. He's a really nice man. Before he died, he came up and he would just talk to me for hours, just like about anything we wanted. It was a lot of fun. So let me just ask you about Hubble now. Hubble, when it looked at Pluto and discovered these two moons, did that come as a surprise? Was there any expectation of finding any new moons when it did these observations, or not?
Mostly what they were looking for was wondering if there was any debris in the system. Okay, because I mean, Pluto and Charon are awfully large, right? Hey, Bonnie's on. All right. Yes, so it's Bonnie Meinke. She just posted up on the thing.
Oh, okay, cool. Hi, Bonnie.
Thanks for joining us, Bonnie. You can answer the questions when I say things wrong. So Charon and Pluto are Charon is 1/2 the diameter of Pluto, so it's a relatively large system. And how do you capture something that's only half your size in the diameter, or it's 1/8 your size in mass? And it's very hard gravitationally to capture something. So it's always been supposed that perhaps there was a collision that caused the capture of this, right? And we've seen in other Kuiper Belt objects that there are families of objects that are associated with it that appears there have been collisions and that they're icy things. And so with New Horizons going out there, we were looking to see if there was debris in the system large enough to worry about with New Horizons. We weren't really expecting to see, certainly not 4 moons, but wondering if there was just some stuff out there. And we're just trying to be careful about it. So
it was a little unexpected then.
Yeah.
Okay.
I mean, the fact that to find 4 new moons was really unexpected.
Yeah, this is really getting to be a really crowded place. So before we leave this image, and I know you want to go to Neptune, and we will, I just want to ask one quick question about this. What is this big dark region in the middle? Why does it look like something's been blocked out there? What is that?
Yeah, I meant to explain that, but you always forget that when you're on a roll. Okay, yeah. So what we're doing is we're showing 2 separate exposures. Okay, so the black bar in the center where we've got Pluto and Charon, the black bar for Pluto and Charon is a separate exposure length, because Pluto and Charon, if we exposed them at the same exposure level that would get Styx and Kerberos, they would blow out the image. Okay. Matter of fact, you can see these little lines across the outer panels. That is, the bleed from Pluto and Charon, their light spreading out into the detector, even though they were blocked out when we took the image to get Styx and Kerberos.
So the exposure time to get the image of Kerberos and Styx visible was so long that then Pluto was comparatively so bright that it blew out the center of the CCD, by blowing it out, I mean saturated it, and making it, basically a splashing light all over the place. And so you replace that, you got rid of that with a lower exposure, a shorter exposure of just Pluto and Charon. Do you have any difference between? You have any idea what the exposure times were on this, or?
Nope.
The difference? Okay, I was just curious what it would take to get some of these moons. Now, this is not something an average amateur is going to be able to resolve, right? Because of the atmosphere.
I'm sorry, say that again?
This is not something an average amateur with their telescope is going to be able to image because of the atmosphere, right? It's just a little too...
Right. I mean, from the ground, even the best telescopes from the ground have a hard time resolving Pluto and Charon.
Right.
Before Hubble got up there, we didn't have such nice images of Pluto and Charon as separate objects. I remember there was an NOAO image of Pluto and Charon, and the two figures of them bled together. So you could see that it was a sort of figure 8 type shape, but you couldn't actually see them as 2 separate objects. That was
Was that from Chile? The mountains of
That
Chile?
was the image I'm remembering was from like 1990, 1988,
Mm,
just before Hubble went up,
okay,
because they were able to do a comparison. Here's what Hubble sees, and here's what you see from the ground.
got it.
Uh,
Okay, awesome. Okay, well now you could go to Neptune. I just wanted to finish
okay.
up with some of that. Thanks, Frank.
No, this is what makes it fun. I mean, I don't have anybody to bounce ideas off of while I'm doing the presentation at the public lecture series. All right, so now we go to Neptune. All right, and again we have that black bar down the center to mask out Neptune. Okay, so it's like a coronagraph. You know, you're blocking out the light of the bright object in order to see the faint things around it. And so at Neptune, what we were studying is we weren't studying moons. Instead, we were studying the rings. Actually, Neptune's rings have these very bright arcs, okay? Just these small arcs of the rings that are bright, okay? And so you can see some over here and up here. You can see some of the bright ring arcs. And Mark Showalter of the SETI Institute was studying these ring arcs, and he's had according to the press release, he had like 150 different images of these ring arcs that he was going through to try and really study and clarify things. And he noticed that he was seeing spots. Okay, now you see these big spots, these three big spots over here.
Hmm.
Well, those are definitely moons. Okay, those are known moons of Neptune. And then there's a spot over here that's also a known moon, but there was other spots that started to appear over and over again. All right, and it was this spot up here, or in the
Well, I
upper
don't know if
right.
that's going to
Okay,
come through, but hopefully it will. Yeah, that's
all
really
right.
faint. It's right where your
That's
cursor is.
right where my cursor is. That's really faint. But let me go to the next slide, and he found that that was a new moon. That it appeared in enough of the images he could track it, and he could then fix an orbit for it, and he got a nice circular orbit, and found that this was a new moon of Neptune.
Awesome.
Okay.
Awesome.
All right. So here you've got the marked up image that throws Neptune in at its proper size, and marks the other moons. All right, and so this moon is, on the next slide, show you that it's part of the system of moons close in to Neptune. All right, and so here's the newly discovered moon amidst all these other moons, and all these other moons were newly discovered back in 1989. All right, so we didn't know too much about the moons of Neptune before Voyager 2 went past in 1989. The only time Neptune has been visited, right? And so this joins in the system where you're in around the rings, and you've got all these moons of Neptune on the inside. The cool and sort of interesting point here is that if you look on the out part, Triton, okay, you can see all of these are orbiting in what we call prograde. They're orbiting, you know, if you want to call that counterclockwise from the way we're looking at it. Triton is orbiting clockwise, or in a retrograde orbit. Okay, it's not orbiting the same as the others. So Triton, the sort of coda to this story is that Triton looks like a captured Kuiper Belt object. Okay, matter of fact,
Mm-hmm.
Triton is about the same size as Pluto, right? So if Pluto had gotten in and gotten captured by Neptune, it would be in something like the same size as Triton, orbiting around Neptune, which just gives you a scale between Neptune and Pluto. All right, Neptune's got moons as large as Pluto is. So I called this story Lunatic Fringe because we're out at the fringe of the solar system, and of course the root word of lunatic is luna, which means moon. All right, so there are still cool things to be discovered. You can still go crazy about the moons at the edge of the solar system. All right.
So what do they know about this moon? Do they know what roughly what size it is compared to some of the others? Or, I mean, they know its distance, obviously, but know anything else?
Yeah, one of the most important things I should have said is that this is so tiny, it's only 12 miles across.
Mm.
Okay, and that's too small for Hubble to really, get any detail on it. But as you follow it over the course of the various things, they're able to get a good estimate of the size as being about 12 miles across. So, I mean, that's about the size of the beltway around a major city, right?
Mm-hmm.
So,
yeah, that's pretty cool. So I guess one of the questions I've always had about discovering moons and inferring their existence based on things like their gravity and whatnot is because these moons are they look anyway so small compared to the size of Neptune. Neptune itself. There's really no way to do that, is there? You know how, like, when you were talking about the precession of Mercury, sort of inferring another planetary body in between the orbit of Mercury and the Sun, you know, here, can you do that with planetary moons at all? I guess it depends on the system, doesn't it? I mean, like with Pluto, you should be able to sort of tell what's in orbit around it, even though you can't see it because it's so small. It might be affected by more gravity than things orbiting it than, say, Neptune would. But I was just wondering if that's something people do to find moons.
I hadn't heard of that happening, actually, but it could be done, first of all, simply because,
Okay.
all right, when Neptune was inferred, it was the perturbations in the orbit of Uranus. Uranus wasn't following the orbit.
That's right.
Right? And so it slightly got ahead and behind, and Neptune and Uranus are about the same mass, okay? So that something of roughly equal mass can have a large enough perturbation to be observed. All right, and so with N1 being only so tiny, even compared to the other larger moons there, I can't imagine that its gravitational perturbation being large enough to notice. But if there was an undiscovered moon that was about the similar mass as the moons that you knew about, then you could see the perturbations as long as they pass reasonably close to one another.
Okay, and I bring this point up because we've talked about it twice now here, and since we're on the subject of lunatic fringe, this is an important concept, especially if you believe in things like Nibiru, folks. If you think there's a planet out there that NASA is hiding, you can't really do that very well. We knew, like as Frank just said, Neptune was discovered long before we ever saw it. We knew it was there. We knew it was there because of what we saw Uranus doing, and yet we didn't, so we knew there must be something there, and then it was finally observed and confirmed that yes, there was a planet out there. So if you think Nibiru, which is something I think people have claimed was the size of Neptune, coming at us, this was back during the 2012 nonsense, and then they were claiming NASA was hiding the planet, which is incredible. I don't even know how you do that. Something the size of Neptune hitting straight to Earth, you're going to see it pretty big in the sky before it hits you. So anyway, this concept is important. This idea that something near something else can affect it, and you can tell it's there based on the things that you can see. In fact, dark matter, the existence of dark matter, is another topic that uses that same concept. So anyway, I just wanted to emphasize that because it's important that people think when the NASA is hiding something in the solar system, you can't. Because of this. All right.
And furthermore, astronomers are egotistical, okay? If we know of something that nobody else knows about, we're going to trumpet it from the rooftops to try and get our names out there, okay?
That's right. You're going to be famous. If Nibiru was really there, then the guy who discovered it is not going to keep quiet about it, right? He's going to be all over the place. And NASA is going to want to feel important, and so they're going to say, hey, NASA is teaching you everything there is to know about Nibiru. Look at Comet ISON, what we're doing for that. We know that's coming around, and NASA's really trying to be a resource there to help you understand the comet and things like that. So that's what would really happen. Not that we better hide it. That doesn't make any sense. And it is, as Frank said, counterintuitive to how astronomers behave.
All right, so we're almost half an hour into this, and we've only gotten to one story.
Okay, I'll be quiet. I'll stop asking so many questions.
No, I love it. I love it. It's
all right, go ahead. I'm sorry.
Let's move to the next story, okay, which I, in my manner, call Globular Clusters, Birth Certificates, and Driver's Licenses. All right, so
DMV
it'll all make
of
sense.
universe.
There you go. Let's start with the globular cluster, okay? This is the globular cluster 47 Tucanae, and this image is not from Hubble. It's from the Digital Sky Survey, and you can see that 47 Tucanae is an amazing cluster of hundreds of thousands of stars all orbiting around each other, okay? And globular clusters, we believe, are some of the oldest objects in the universe. It used to be when we age dated these globular clusters, we got them as being 17 or 18 billion years old, which is kind of funky when you think that the universe is only 13 or 14 billion years old. How can we have a cluster of stars older than the age of the universe? But we have since then resolved the discrepancy, and we still get that the age date for these things is slightly less than the age of the universe. And so you've got these incredible number of stars, and you can see that right here in the center of this globular cluster, that from the ground, it's really blown out. Okay, you can't see much detail because there's lots of stuff. But if we take Hubble and we take a much smaller much shorter exposure, we can see detail. And so this is a Hubble image inside for detail inside 47 Tucanae, which is really cool. You can see the individual stars, and Hubble's high resolution helps us measure the details and the characteristics of these stars much closer into the center than other telescopes. And so when we study the stars in these details, we get a slight variation on the story that we had. Okay, we've seen that the stars have slightly different metal contents. Okay, the chemical compositions are slightly different, which indicates that perhaps there were multiple areas of multiple periods of starburst. But we couldn't really prove things like this. All right. So in order to do this, in order to age date things, we do what we look at the Hertzsprung-Russell diagram. Okay. Now that's a big mouthful of a word, the Hertzsprung-Russell diagram. But let me show it to you in a video. Okay. All right. Let's play this video. All right. So this video is going to look into a different globular cluster. This is globular cluster Omega Centauri. And this is a Hubble image that goes into the ultraviolet to get the blue and goes into the infrared to get the red, but it's really good for showing off the development of the Hertzsprung-Russell diagram. So here we're just zooming in. All right. Now let's take this image and let's manipulate it to put all the blue stars on the left and all the red stars on the right. We're sorting the images in terms of the bluest to the left and the reddest to the right.
Okay, Frank, we're getting a lot of drop frames here. I'm not sure if that's the playback.
A lot of drop frames.
Are you seeing drop frames on your computer?
I was not seeing drop frames on my computer.
Maybe this is the problem you said was sometimes happens on Macs. Can you try that one more time?
Let me. How about if I? There we go.
Yeah, I don't know if you can see then the bottom window of the Hangout.
Right, I see it. Okay. Well, how about if I'm just gonna pause it there. Okay.
Okay.
All right. So now you can see this. So that was taking the image. Let me go. Actually, I'll do it like this. Okay. So here is the image, right? You got lots of blue stars, lots of red stars. Okay. And about here. All right. There you go.
Yeah.
Then if we separate all the blue stars to the left and the red stars to the right, you can see we've sorted it that way. Now we're going to sort and take the brightest to the top and the faintest to the bottom. Okay. And that should be somewhere about there. There you go.
Nice.
Okay. All right. Now, it's really cool when you animate that. You actually get to see the stars move across the screen left and right, and then move across the screen top bottom. And you produce this diagram where you have color or temperature on the x-axis. You know, red to blue is actually a color, but it's actually a temperature axis, and then faint to bright going on the vertical axis, right?
So I'll tell you what I'll do. I will. We can post this on the YouTube channel, on the Hubble Site channel, YouTube channel, and the playlist that we have for different animations. And you guys could maybe watch it after the Hangout's over. I'll see about getting it put up there.
This was released as part of one of our press releases, so I'll find the link and make sure I post it in the chat window.
Okay. All right. And we'll do that as well. Well, yeah, post that in the chat window.
Okay. And so the HR diagram. The cool thing about it is you can see this long diagonal line here of stars. Okay, and that's what's called the main sequence.
Okay, well, Frank, you better start with telling us what the HR diagram is, what it does.
Well, I mean, I guess I was trying to do that because.
You're going to do it this way. Okay,
right.
All right.
Well, as they've got the temperature versus luminosity or brightness. Okay.
Oh, okay.
Okay, and the main feature is this main sequence along that runs diagonally top left to lower right. Okay, and stars that are in their major life, the major part of their life, are fusing hydrogen in their core, occur along this main sequence. And as they start to die, they move off of the main sequence in their plot on this diagram, and over to the upper right, they become these red giants and red supergiants. And the blue here is the instability strip. But the point is that the stars that are just beginning to die are at the top of the main sequence. And so where that main sequence exists, you know, that you can start to tell stellar ages based upon the main sequence and the HR diagram of a globular cluster.
Nice.
Okay.
So this is just a classification of stars based on their brightness and their size, and where they are in this chart tells you where they are in their life cycle.
Exactly. And so by studying the HR diagram of these globular clusters, we've been able to tell that, well, maybe there are two separate populations, okay, and they're slightly different in age. And we'd seen a little bit of chemical composition differences, but we needed more. And so with Hubble, we could study not only the chemical compositions and characteristics, but because Hubble has such high resolution, we can actually resolve the motions of these stars. Okay? And so we took pictures about a decade apart. I think it was actually 8 years apart. And we were able to tell the motions of these stars and figure out, are they doing circular orbits or are they doing radial orbits? And what we found is that there actually were two dynamical populations. Okay? And so on the left, this is our artist diagram of the quote red population, and I got to say the red is just only a tiny bit redder than what we're going to call the blue population. Okay.
Okay.
And the orbits that we found for these are more circular. They're more randomized, going in every direction. Okay. And the blue population shown on the right was more centrally concentrated, and their motions were more radial. Okay, they had these highly elliptical orbits extending radially outward from the center. All right, instead of having the more circularized and randomized things. And so this, along with the chemical differences, gave us a good reason to say, hey, there really are two good evidence for two stellar populations in this globular cluster. Okay, even though they were born 12 billion years ago, it looks like there was a first population that when the globular cluster formed, most of the stars were part of this first population, and they got their randomized orbits. But as the gas collected to the center, about 100 million years later, you got a second population of star formation, a second burst of star formation, and those stars formed more towards the center. Hence, they're more centrally concentrated. And then when they got their randomized kicks, they would end up on more radial orbits. So they're bluer because they're slightly younger. I mean, just a touch bluer, so they're slightly younger, they're more concentrated, and they have more radial orbits. And so this is the first evidence of really good proof that there are more than one stellar population in these giant globular clusters. So do you have anything to question on that, Tony?
No, what I'm doing right now is I'm putting a link to the animation that was blocked out. I think I got the right one. It's the press release from Hubble shows link between stars' ages and their orbits in dense cluster. Is that the right press release?
Nope.
Oh.
Nice try.
Oh.
Oh, the press release. Yes, no, the video isn't in there, but yeah, that's the correct. That is the press release.
Oh, okay. Well, there's something about a zoom in into 47 Tucanae, but
right, yeah, that's okay. A different thing.
Okay.
I will
Sorry,
go
guys.
right now. That's all right. I will go right now and find the thing. It's the Omega Centauri one.
Okay. I'll. Okay, so well, we can put that in after the fact. I just wanted to. I was trying to do it while we were talking about it. So go ahead.
Okay, so this is just kind of cool that in these globular clusters, which we considered to be these really old sort of monolithic stellar populations, we're now getting the resolution with Hubble to be able to subdivide their populations.
Awesome. That's really great. No, I don't really have any questions on this one because I was. I was sort of trying to get the animation going. Yeah. Me and my multitasking fail. Okay, go ahead.
All right.
So the next story. Oh.
The next story is one that you'll love because we definitely want to talk about it. It's our reaction to Kepler.
Oh, reaction to Kepler.
Okay. All right. We'll explain the pun there.
I love your titles, I have to say.
All right. So. We are looking at this image here is an artist's conception of the Kepler mission, and just to remind everybody what Kepler did, has done. It was launched in 2009, and it was designed to study planets transiting across the face of their star. Okay, so in the upper right-hand corner, you see this star, and you see this planet with a lovely black line across it to show the idea of a transit. Now, of course, Kepler can't see the planets actually doing the transit. What it measures is the light curve, the dimming of the star, and if it matches a certain pattern, then it can say, oh, that periodic dimming of the star could be due to a planet crossing in front of it, which we then have to confirm. All right, and the cool thing about Kepler was that Kepler had studied a lot of stars.
About 150,000 or so, right?
You're getting ahead of me. You're perfect.
Sorry.
That's on the next slide. All right. But anyway, so each of these squares here is part of the Kepler field of view, is one viewing point in the Kepler field of view. And so you can see that there are about 20 different fields of view. All right. And in that region, it was able to look at more than 150,000 stars in that field of view, and studied them for more than 4 years.
That's right. It didn't look anywhere else. It only looked in that same spot in the sky, so it didn't have to try to mimic the entire universe.
Exactly.
Or galaxy.
All right, and so it was studying these stars over and over again, taking pictures of them every night for 4 years, and looking for these dips in their light that had the characteristics of being planets passing in front of the star. Right, and so from these 150,000 stars, they came up with approximately 3,000 candidates. At the beginning of this year, it was 2,740. I'm assuming that there's a few more by now, so I put roughly 3,000 candidates. And then in doing follow-up on those candidates, they have gotten 150 confirmed planets, which is really kind of cool.
Mm-hmm. And how was that confirmation done?
Well, you've got to be able to do, there are a number of ways of doing it. They get a little technical. The transit timing variation technique is one in terms of checking the timing of it.
Okay.
And if other telescopes can, of course, come in and help do the confirmation. I'm not an expert in confirming these things, but
but Kepler would go out and say, you know what, these 3,000 or so stars might have planets going around them. You might want to take a closer look at these guys. And so people, in a variety of ways, go out and do that. Whether it's in the telescope, maybe they look at Kepler's own data closer. To find these planets, or there's probably all kinds of different ways of doing it. But the important point that you're making, and I agree, is that this is looking at a huge amount of stars over 4 years, and it's gotten quite a bit of data over that period of time. So,
yep,
they're still combing through it.
Yeah, and the point is they are literally looking at a haystack and really searching to find the needles with it. And sometimes you'd say, oh wow, that can't be a very efficient technique, but when you design it ends up working really nicely.
Yeah.
Okay. So what's the problem here? All right, well, the problem occurred in May of this year. All right, whoops, my cursor isn't where it needs to be. There we go. All right. In May of this year, the reaction wheel number 4 indicated a failure. Okay, and it was announced on May 15th. Okay, so you can see where it says unambiguously indicate a reaction wheel 4 failure. All right, why would that be a huge problem? Well, first of all, a reaction wheel is the way that they point the telescope. All right, and its name reaction wheel comes from Newton's law, where for every action there's an equal and opposite reaction. Right. So if you spin the wheel one direction, powered by a motor, right, then the telescope turns in the other direction. And since you've got these 3 axes, X, Y, and Z, 3 independent axes, you need 3 reaction wheels to point the telescope really carefully and align it to look at the stars, right? Well, reaction wheel wasn't the first reaction wheel to fail. One of the reaction wheels had previously failed. And so with this failure in May of 2013, they were down to 2 reaction wheels, and with 2 reaction wheels you couldn't point the telescope as carefully as you needed to do the primary mission of Kepler. Well, of course, we're not. We astronomers aren't going to give up, okay? Because this is an amazing mission. It's produced an incredible amount of science already. We want to keep it going. So we studied and studied and studied over the summer months. But unfortunately, last month, on August 15th, it was announced that they were ending the attempt to fully recover the Kepler spacecraft. All right. They had tried a variety of tests to try and see if they could get the reaction wheels to do what they were supposed to, and they gave up, unfortunately.
Yeah.
All right.
But you know, they had entered. I think you said this. They had already done their primary mission and were on their extended one when this happened. So they had already gotten what they had intended to get from Kepler, correct?
Right, and that's the thing. Is the first of all, that's the first point to make. Is Kepler was a complete success. All right, the mission was designed to do 3.5 years worth of studying of these stars. All right, and they'd already gotten over 4 years worth of data. So
I know, but you know the thing is, Frank, we all get attached to these things, right? Like we launch them up there, they show us things about the universe we didn't know before, and then we fall in love with them, and we don't want to ever have them go away.
Exactly.
Hubble got us on that, I'm afraid.
I know. I mean, when I think of the kids in my kids' school, they've never known a universe where there wasn't a Hubble.
Oh, that's not a bad thing. That's really good.
That's a fantastic thing for astronomy. But I mean, they're so used to Hubble always producing cool images. My son wasn't born until 1996, right? And so Hubble was not only there, but it had been repaired and was already producing the amazing images.
Yeah.
So we have gotten used to Kepler over the last 4 years, but now we are going to have to try and do something else with it. Okay. But so the first point being that it's got its full data, and second point being that all of that data hasn't been analyzed yet. Okay, as you can see here in the press release, it says will take many months to process and years to analyze. This is a tremendous amount of data. When you think of 150,000 stars over 4 years, there are an incredible number of data points to work through and to process, and you're coming up with new computer algorithms to help spot what you're looking for. As computers get faster, so you can come up with new ways of analyzing it as well. So there's plenty more to do, and there will be more results. Matter of fact, just as to accent that, on August 29th, just a few days ago, 14 new Kepler planets were announced, and these were using the transit timing variation technique to confirm them. And so that brought the total count up to that 150 that I said a couple slides earlier. All right.
Awesome. So it is still, the planets are still coming in. We still got a lot of stuff to go through.
All right. It may be the end of the primary mission of Kepler, but it's not the end of Kepler discoveries. Okay, we're still going to get a lot more as we learn to follow up. Furthermore, they're now considering what new science research Kepler can carry out.
That's right, because Kepler is down, but it's not out.
Right, it's still a very nice telescope up there, and we know the control software, we know the data reduction techniques. It has a lot of its characteristics are well known, and if we can apply it for other science missions, other science ideas, we certainly will do so.
Right.
It's not like it needs to be mothballed immediately.
Right. So so I guess NASA asked for a list of ideas from astronomers on what they could do with this thing. It is a space telescope. It can still do stuff. It can still gather photons. So what photons do you want it to gather, and what kind of science do you want it to do? And they got, I guess, from what I understand, a really good response. And so they're going to make a decision on that, I think, in 2014. Is that right, Frank? On what they're going to do with it?
Yeah. So we astronomers are pretty careful, and they put Kepler into a mode where it's going to use as little fuel as possible. Conserve any of the consumables on it, conserve those while they study what science can be done.
Do you happen to know if you can point it to other areas of the sky, or are we still looking at Cygnus with this?
I'm pretty sure you could probably point it to where you needed to.
Okay, I'm just curious. I think
it's not designed to slew very, very far across the sky.
Right.
But if you
they weren't intending to slew it at all, I don't think.
Well, you need to slew it just a little bit to cover the various fields, right?
Yeah.
And all the detectors and such, and make sure you can actually point it. But no, the slewing is not its forte.
Right. Okay. Well, yeah, it'll be cool to see what ends up happening with this mission and the telescope itself in the coming year. So, Frank, you want to get to some comments, or did you get to cover? Did you cover everything?
Yeah, let me just finish up
Okay.
with
Oh, super.
the advertisement for the public lecture series.
Okay.
Okay, there's our website, hubblesite.org, About Us, Public Talks, and you'll see on there the list of the upcoming talks. Although those aren't the current ones, you showed that website earlier.
Mm-hmm.
And I just wanted to advertise that there's an archive back to 2005. So we've got 8 years of
Yeah,
these public lectures.
and they are really interesting. I've been to several of them, and I've watched a lot of them online. These are all done on the first Tuesday of the month at 8 p.m. Eastern Time, right?
Yep, the only exception is when a holiday occurs on the first Tuesday, like July 4th, or when Election Day is on the first Tuesday, some Novembers.
Okay, so special things like that might prevent it from happening, but usually that's when they're held, and they are also webcast, correct?
Right, and that's what the archive is
Okay.
the STSCI has a wonderful webcasting team, and they put them out for that. And finally, the last slide here is just the advertisements in October, where John Deb is going to talk about raising Fomalhaut B from the dead and other high contrast adventures. I've got myself slated for the November talk because Comet ISON might be amazing. And even if it's not, I gave myself a cool title, Interplanetary Invaders Bringing Spectacle and Devastation. And then in December, Stephen Holland will talk about gamma ray bursts. So we got all sorts of cool things to
that
talk
is
about
cool.
there.
And we've had John on before. We've done a hangout with him in the past, guys. So you've seen him before, and he's an awesome speaker. So you don't need to be in Baltimore to watch these, but I would, but I highly encourage you to give them a shot and check them out because they are, while they're geared to the general public, you can get in depth, and usually the topics they get into are and the audience that attends really asks some good questions, so they kind of get really deep into some of these topics. Okay, Frank, let's get to a couple of these comments. I'm on YouTube right now, and I have from Luca Modern Talking goes, I have a question. When Hubble takes a picture of a cluster of stars, can Hubble spot a shooting star crossing the cluster?
Yes. We have actually a bunch of Hubble images that have meteor trails. I know of one in particular that was a very nice shot of stars that had a meteor trail on it, and I'll try and find it on News Center and post it up for you. But we will often get meteor trails across some of our shots.
Okay. So Michael Jobin goes, I like star globs. Okay. Kind of like it said, I like turtles. Okay. All right. So also from Luca Modern Talking, I'm on YouTube again. What satellite is monitoring the path of Comet ISON? There isn't one effort that's just keeping constant watch on it. We've got a lot of different things. Hubble is slated to do some more observations in October, I believe, but there's all sorts of ground-based and modern or amateur astronomers that are monitoring it. So it's a whole bunch of things, a whole bunch of people that are doing it.
Yeah, I mean it's not just one; it's a lot of them. And Hubble had to stop looking at it over the summer because it was too close to the sun. And now amateurs and people from the ground who can get closer to the sun than Hubble can look at it starting now. Hubble has to have a good angle between the sun and the object it's looking at, so that it doesn't hurt the instruments in there. So it's sometime in early October we will be able to get back to looking at it.
Yeah, Tim Egrid from YouTube says, or Tim.egrid. Boy, some of your usernames, guys. So he's like, it's sad, so sad that Kepler's primary mission ended, but yet hopeful that it has provided us with so much data that we will have to check through. That's true, and it's important to remember. It's like I know we get caught up and we get emotionally attached to these things, and we love them that they're up there, they're showing. And I think part of it is that we get them up there and they take pictures, and we just kind of stare at them and go, whoa. and they just blow our mind constantly. All of these things. Exactly. Spitzer, Hubble, Herschel, the Planck Space Telescope, to me, was a mission that blew me away. The way they mapped the cosmic microwave background to a degree I couldn't believe when I saw the final map they came out with. So these missions really kind of get under our skin, and it's hard to let them go. It's hard to watch them die. When the sad day comes for the end of Hubble's mission, of course JWST will be up there, but it's still going to be, interesting to watch the world's response. And I'm reminded of the fact that John Grunsfeld, when he was up there servicing it the last time, they put this sort of universal adapter ring on it that just to make it as easy as possible for something besides the space shuttle to maybe grab it. So I'm sure there'll be renewed interest in that little ring at the end of Hubble's mission. So.
John Grunsfeld's a huge proponent of developing robotic servicing missions.
Yes.
So he would love to be able to send robots up and bring Hubble back, but I don't know if that, we have no idea if that technology will develop in our lifetimes enough to enable that.
Yeah, Frank, I was just at the Atlantis exhibit in Florida at the Kennedy Space Center, and one of the things they had there as part of the exhibit, it was really beautiful, by the way, was they had a full-scale model of the Hubble Space Telescope sitting there. And
right.
We always say it's the size of a school bus, and it's up there, doing school bus-sized things, but that thing is really big. I mean, I couldn't believe it. I was standing underneath it. It's like amazingly huge up there. So,
and it's perfect to have right next to a space shuttle, simply because it's the largest thing that can fit into the space shuttle cargo bay, right?
I know it took up every inch of that thing. So it was. I don't know. We always do, like with James Webb, with JWST, we're saying, the sun shield is the size of a tennis court, and of course, when you go to the full-size scale model, you're not thinking tennis court when you're looking at that thing. It's just like, whoa, that thing is enormous. It's huge. So the amount of work that goes into these space telescopes are really great. Do you know how big Kepler is compared to Hubble, by any chance?
Kepler is about the same size as Spitzer.
Okay.
So it's like a meter and a half size mirror.
So they're smaller than Hubble by some. We don't really know exactly.
Yeah, at about 1/3 the size of Hubble, if I remember correctly.
Oh, okay. Yeah. So these things are pretty expensive to get up there. So lighter is better. So the kind of effort that goes into getting these giant space telescopes up there. So. So yeah, I think I'm going to be. Well, I don't think. I know I'm going to be very interested in the new stuff that they figure out to use Kepler for. I can't wait to find that out. And like I said, I think I saw they're going to announce those results. They're pouring over all the proposals now. They should know something by, or they will know. They will announce something by the 2014 timeframe, maybe in September, something like that. So I think that's it for the questions. A lot of comments. Kim Rasmussen from YouTube goes, "Wow, what happened? Information being shared? Hell have frozen over." So
let's see. Do we have anything? All right. Charles Bell on the Google Plus page would love to see the HR diagram video. I did post the link on the Google Plus page. I also just posted a link to an asteroid streaking across a star field picture from what was that? 1999. Okay. Heidi Kahn has made a lot of comments and
yes,
nice
thank
things. Thank you, Heidi.
Yeah.
Let's see. Will MAG-AO be able to better resolve S2004 and 1? I assume that MAG-AO is talking about adaptive optics, such. Adaptive optics works well in the infrared. And N1 probably does have some emission in the infrared, but I don't know. Adaptive optics can be tricky as to what objects it can be applied to.
Yeah, for those who don't know what that is, that's just a series of mirrors that are used in ground-based telescopes using something like a laser as a guide star to kind of cancel out the effects of all the atmospheric distortion of the waves, and they actually do a pretty good job. They can get as good in some cases as space telescope images do.
Yeah, but unfortunately it doesn't get down to visible light. It's in the infrared as where it's best suited these days, we're hoping to over the course of this decade, before 2020, get down to seeing into the red end of the of visible light using adaptive optics and getting Hubble type resolutions, which would be really cool. Okay.
Yes.
If adaptive optics, by the time Hubble retires, could actually do a decent amount of what Hubble can do from the ground. But that would be real nice.
Okay, so just one last question, and then we're going to sign off here. Galaxia from YouTube is asking, how is TTV different from the normal, the quote normal transit method? And I don't, based on what you said before, I'm not sure you know that one, Frank. But you want to give that a try?
I'm quite sure I don't know that one.
Yeah, I don't either, unfortunately. So I can't help you there.
But if we do this next month, I will look it up, and
yeah.
I'll write it down right now.
Yeah, we'll get that down. We
Okay.
don't. We work in like. There's so much that can be done with these exoplanets, and the way in the details in which they're finding these out, confirming these planets is pretty varied. So we're not experts on all the different methods. Lately, they've gotten, the kinds of methods they use are things like the transit method is just one of, I think, about 3 that most space telescopes are using these days. So there's just as many. There's a lot of ways to just find the candidates even. So confirming them has got all kinds of techniques associated with that as well. So
okay. I will just say that there's a very short article on Wikipedia about transit timing variation. So try going there to see if that makes any sense to you. All right, let's talk about using it to discover Kepler things.
And we will address that too. We have plenty more hangouts in store for exoplanets coming up, and we will definitely explore these some of these techniques and questions in future hangouts. So, Frank, I want to thank you. This was a lot of fun. Thanks for doing this for us. Let us know what you guys think. If you guys like this idea, if you guys want us to keep going, we'll be back next month. So please leave comments, leave questions for us on this event page, on Facebook and Twitter and all these places, and let us know what you thought. Frank, thanks, man. This was great.
Thanks, Tony. It was a lot of fun. I knew we'd have a blast, and it's so much fun being able to bounce ideas back off somebody while I'm doing this news presentation, because when I'm doing it live in the lecture hall, it's just me, and all I get is sometimes I get a few laughs, on my jokes. Not always, but having
get a
conversation.
Well, I'm a good audience, so I'll definitely laugh at your jokes. I'll also groan at your puns and everything. So yeah, this was a lot of fun for me too. And let's don't forget, guys, the Public Lecture Series, first Tuesdays of every month. Start watching them on the webcasting website, and let us know what you think about those as well. You can't leave comments there. You can on YouTube, and I'm considering finding out about getting those posted there as well. We'll find that out. I'm not sure about that yet, though. So that's it for this time. Hubble, almost said space fans. That's that's it for this time, Hubble Huggers. Thank you guys for watching, and as always, keep looking up.
All right. Bye-bye. Comes from, we're talking about the solar system. Okay. Now, can you see my mouse pointer on this, or do I have to use something?
I can see it.
You can see it. Okay.
It's being embiggened, so I think it's showing up.
Embiggened. He's using the Simpsons word. Okay, so down here toward the sun in the center of the solar system, all right, not even shown on this plot are Mercury, Venus, Earth, and Mars. They're way down tight in, grouped in around the sun. And what we've got in this plot here is the orbits of Jupiter, Saturn, Uranus, and Neptune, and also the former planet Pluto, which, as you can tell, one of these things is not like the other. It's easy to tell which one is Pluto. So the fringe aspect of all this is that we're going to talk about things out at the fringe of our solar system. And the lunatic comes in that you may remember that Hubble has actually been studying Pluto really carefully, prepping for the New Horizons mission. Because the New Horizons mission is the first space mission to go past Pluto, and it's going to get there in about 2015. It actually was launched in, what, was it 2005 or 2006? Do you remember, Tony?
I think it's about 2006, I think. I'm not. And so I have here, so I put the link to our public lecture series is on the event page, as well as there's also a link to the archive of past webcasts of the series as well. And as part of this, and here you can see a picture of Frank. What are you doing there? Is that like a shadow puppet thing, or what are you doing?
I
Doing
think
shadow puppets?
I think when they got that picture, I wasn't prepared for it. First of all, that wasn't posed. I guarantee you that. But all I was doing was I was counting off. Okay, 1 reason, 2 reasons, 3 reasons. So I was saying, well, 1 is this, and this looks like I'm on number 2 because I got the second finger, and I probably was doing 3 or 4 different things.
It looks like you're trying to make a bunny rabbit to me, but anyway, okay. Well, I'll take your explanation for now.
Okay, actually, what I'm doing is shadow puppet of an accretion disk around a supermassive black hole.
There you go. That's it. Now, see, you're not the outreach astronomer for nothing. That's called quick thinking right there. Okay, so anyway, the idea was we were talking about this, and Frank gives these prior to the lecture. He gives a little presentation of his own where he introduces some new things that are happening both in the world of Hubble and in space science and astronomy in general. And so he said, why don't we do this in a hangout so that we can make it available to more than just the people who show up at the institute. And so that's what we're here to experiment with today. We're going to try this out and see if you guys like it. And if you do, if you respond well to it, we will continue doing these probably on the Wednesday following the public lectures that happen on the first Tuesday. So let's try to look for those. Let us know what you think of this. If you find it useful, if you find it interesting, and you want us to do more, we'll be happy to keep going. So how do you tell us what you think? Well, this is the land and world of social media, so you have more than enough ways to interact with us. If you comment on the event page, which this is being broadcast from on Google+, we will see those comments. And so if you have any questions for Frank also, that's a good place to leave them. We're also monitoring Twitter and the YouTube comments that we're broadcasting from the Hubble Space Telescope's YouTube channel. So those are all the different ways you can interact with us, and you can also try Semaphore, but I may not see that. So let us know what you think. Comment, leave us some comments and questions, and we will sort of listen to what you have to say as far as whether this was something you found useful. So Frank, let's go ahead and get started. What do you have for us this week? So you have some stories that you think are particularly interesting for this month. So why don't you go ahead and introduce them to us? Hello, Hubble Huggers. It's time for another Hubble Hangout. I never get tired of saying that. My name's Tony Darnell. I work at the Space Telescope Science Institute, and we are about to start another, sort of a new series in Hubble Hangout land. We were talking a few weeks ago, and my guest here today, which is Dr. Frank Summers, is the outreach astronomer. Hi, Frank. Welcome.
Hey, how's it going?
Good, thanks. So Frank and I were talking the other day, and Frank reminded me that every month he does this. He hosts a public lecture series at the Institute where it's held on the first Tuesday, right, of every month. Is that right?
Yeah. The first Tuesday of every month we get a different astronomer from either inside the Institute or a visitor coming, and we get them to specially prepare a talk that is more general. And specialized to present to the public. So they get to talk about their scientific research, but we remind them that, all right, you got to start from the basics, get the public, bring them up to speed, but you get to go from sort of the basics of a topic all the way up to the current research that they're doing. Okay, so what I do every month is I try and come up with news from the universe, which of course has to be Hubble-centric because, hey, I get paid to talk about Hubble, right?
That's right.
That is my job, but I don't like it only being about Hubble. So when there are other cool stories that aren't necessarily Hubble-centric, I sort of sneak them in as well and show off all the pretty pictures and try and explain the science. So let me do my screen share. All right, and get to my PowerPoint. And there we go. All right. So this is the presentation that I present. It's called News from the Universe, and as you can see, this is for September 2013.
No, you're not doing it right. You have to go News from the Universe.
Universe.
Nice reverb. All right.
Well, you need 2 people to get that reverb in there correctly. All right.
News from the Universe.
And I also have a lot of fun with it, okay? Because my first story, the top story tonight, is called Lunatic Fringe.
I love it.
And it plays off on both words, lunatic and fringe. And the fringe part